In this video, we're going to look at something called expected value. We're going to understand how expected value takes into account both probabilities and winnings when we talk about games of chance. We're going to be analyzing games of chance with expected value, and then use it to make decisions based on these games and other situations. And we'll be talking about expected value in different situations other than just these games. But to start, let's talk about a common game, and that is roulette. So in roulette, there is this wheel filled with different numbers and colors. A marble is put on that wheel. It lands on something, and different payouts happen depending on what people bet. There are 38 numbers, 1 through 36 colored half red and half black. And then there are two special numbers, 0 and 00, both colored green. So you can bet on a marble landing on one of the colors, or a number, or a series of numbers, and you get different payouts depending on what you have. You get a bigger payout if you guess exactly what number, smaller payout if you guess the color. So if you do bet on a marble landing on black, the house pays out at 2-to-1 odds. And what that means is that if you bet $10, you get double that back. So that is a net, we should make clear of that. You net plus $10 because you had to put 10 in, and you get that back. So you get 10 plus your money back. But this is what the house pays out. The house is another name for the casino. The casino gives this money back, but that doesn't match the actual probabilities that you'll land on black. If it were that case, the casino would never make any money because it would always be exactly what would happen. It would always come out kind of even. So the odds of actually getting black on a roulette wheel are 18 out of 38. There's 18 black spots, 38 total spots. That's going to be about 0.474 chance that you're going to get black. So you should expect to win the bet that you place on black 47.4% of the time over a large number of plays. So the question we're going to ask is, what would you expect to win or lose if you played this game a whole lot? And then if you think about each time you play, what's the average number of winnings that you have? What's the average profit that you have? And this is what we're going to be calling expected value. So let's think about this real quick. There are two things that could happen. We could have the marble land on black, or it could not land on black. Those are our only two options here. The only things that we care about. There's obviously lots of different things that could happen, but that's the only things we care about. Land on black or not land on black. It's going to land on black 47.4% of the time. And it's going to not land on black 100 minus 47.4, which is going to be 52.6% of the time. If it does land on black, we win $10. We get $20, which is just covering what we put in, and then $10 back. And if it does not land on black, we lose our $10 bet. So overall, this is going to be plus $10. This is going to be minus $10. So how can we put this into one value that kind of tells us what's going to happen? And this has to do with the probability that we're going to win or lose. It's not half and half, and if it were half and half, then we would always just come out even in the long run. But 47.4% of the time, we win $10. So we're going to take that 47.4. We're going to write it as a decimal always. I should make that clear. This is 0.474. This is 0.526. We're going to take that value and we're going to multiply it by our result, our plus 10. We're also going to take our 0.526, that's the chance that we're going to lose $10. We're going to multiply them together, and finally we're going to add those two values together. And if we do that, we can do this. It's going to be 4.74 minus 5.26, which is going to be about negative 0.52. And this is what we call our expected value. And we'll talk about that calculation more on the next page. So what the expected value is, the expected value of an experiment is the average result we should expect if we repeated the experiment a large number of times. We shouldn't really expect to lose 50 cents, 52 cents any time we play. In fact, it can't happen any time you play. But on average, that's what you would be losing each time. So if you played 100 times, each time you would expect to lose 52 cents. So we could take that value, multiply it by 100. We should expect to lose $52 over 100 times that we play. Right, so the expected value is this one time, like each time you play the game, that's how much you should expect to win or lose. And yes, you should expect to lose money when you're playing roulette because the odds, 0.474, are less than the odds that you kind of get back. Right? The casino is like acting like it's 50% chance that you get black, but it's not actually a 50% chance. So let's look at this a little more carefully here and how we're going to calculate expected value. So to calculate the expected value of an experiment, we're going to label expected value as E of X. Make a chart where you list each of the experiment's possible outcomes, their values, and their probabilities. And it is important that we list all possible outcomes. On the previous one, we did black and not black, and that covered everything. There was nothing left out. So we're going to look at their values, their results, in this case, the money that we get back, and the probability that each is going to happen. We're going to multiply each value or result by its probability, and then add those values together. So let's look at the same question. What is the expected value of profit if you bet $10 on black on a roulette table? So here we're actually going into three different parts. We're not doing black and not black. We're doing black, red, and green. But note that's the same thing as doing black and not black. So our expected value, E of X, we take our result, our plus 10. We win $10 18 out of 38 times. We expect that to happen. We expect to lose $10 minus 10, 18 out of 38 times. And we expect to lose $10 2 out of 38 times. And we can see that these two values actually cancel out. It's going to be 180 over 38 minus 180 over 38. We're going to be left with here a negative 20 over 38, which is going to be exactly negative 0.52. I should say this is approximately negative 0.52. Same calculation we did before. Okay, so we take the result times the probability, and we add them all together. And this is telling us what we should expect to happen each time. So now we need to kind of talk about, this theoretical mathematical thing that we have, this expected value, and then what kind of happens in real life. So expected value is not a guarantee. And in real life, the actual winnings could be much different, especially with a low amount of repetition. right? If you just play a game once, you're never going to get minus 52 cents as an outcome, right? But it's just an average kind of thing as we get. If you would repeat more and more and more, the expected value becomes more and more accurate. So this is how a casino operates, right? Every casino game, without fail, every casino game has a negative expected value for the player. A good casino game for the casino gives the player a belief that the odds are good to win, but the expected value is always negative and always negative enough so that the casino profits, and in a big way. And roulette is actually a really good example of this because when you look at this roulette wheel, you have this idea that it is half the time it's black, half the time it's red. There's maybe a small chance that it's not that, but with time you think about it, it's just half and half. So if you put, $10 on black, you should expect that half the time you're going to win. That feels good. It feels like you have a good chance. But in the long run, you'll just lose money if you keep on doing that strategy. All right, so let's look at another thing for roulette. What is the expected value of betting $5 on a single number? So there are 38 numbers total. What's the expected value of betting $5 on the single number? The payoff here is 35 to 1 for such a bet. That is, if you bet $5, you're going to get back 35 times $5. And this is actually minus the $5 that we spent to play. So what is the expected value? Well, our two outcomes are that the winning number appears or the winning number does not appear. Any other number comes out. Our expected value is going to give us our results times our probability. Note that the result here is we get 5 times 35 minus the $5 that we spend. That's going to give us 175 minus 5. That is, we're going to gain $170, which feels pretty good. So here our result is plus 170 if we get that one number, but that only happens 1 out of 38 times. The rest of the time, we're going to lose just $5. That's going to happen 37 out of 38 times. This is a much different kind of bet than the black and red kind of idea. Right? That one, it's like a really good chance that you might win a little bit of money. This one is a smaller chance that you win a lot of money. So let's do this calculation. Note that if you keep it as a fraction, it can be actually much easier to calculate. This is 170 over 38 minus 185 over 38, which is going to come out to be negative 15 over 38, which is going to be about negative 0.395. So here you expect to lose 39, almost 40 cents. Let's just round it to 40 cents each time you do this strategy of betting one number. So now it raises the question of, if you're playing roulette, what's more advantageous, to bet on black or to bet on a single number in roulette? And if we look at just expected value, the answer is to bet on a single number in roulette, as the expected value is bigger than if you would on black. You would expect to lose less money that way. Right? But then there's some more kind of things at play, some more psychological kind of things at play. Do you expect to play this game a whole lot? Or do you expect to play it just a few times? If you expect to play a few times, you'd expect to win, some more times playing the black-red strategy. Maybe you wouldn't win as much playing the one number strategy. But mathematically, you would expect to lose more doing the black and red strategy than the single number. And the math is this expected value, this value that kind of gives us this idea. So as I said, all casino games from all casinos have negative expected value for each and every kind of thing that you could do. Some games have, worse odds for different things. I think the best odds that you can have come on a craps table. There's a few things you could do, but they're still negative. You should still expect to lose each time. And the idea that with more and more repetition, the expected value becomes more and more accurate, this is exactly how a casino makes money. So you might think that if you go in and you get lucky and you win a huge payday, a jackpot or something from a slot machine, the casino doesn't care. They're all good with that because with enough repetition, with enough people coming in, the losses that other people have will counterbalance that big payday that happens. So let's look at another example, this time moving away from the idea of games of chance and talking about insurance. So an insurance company insures a house worth $250,000 for an annual premium of $500. If the probability of the house being destroyed is 0.0015, and assuming either total loss or no loss, we'll talk about what that means, what is the insurance company's expected annual profit for the policy? So let's talk very generally about how we think about insurance and how this kind of works in a very, very bare bones kind of sense. You pay an insurance company a certain amount every month, every year, whatever it is, so that if anything bad would happen to your house or your car or your life, whatever it is insurance you're talking about, then you would be compensated to cover that cost. So what this is saying is that you pay $500 each year, an annual premium of $500, so that if anything would happen to your house, you would get compensated for the appraisal of the house, for the cost of the house, in this case, $250,000. So in the eyes of the insurance company, we're talking about the insurance company's expected annual profit. There is a small chance that the insurance company has to give $250,000 out to pay for some damages to a house. Then there's a very large probability that they don't have to pay out anything and they just get $500 for not doing anything. So let's think about what that probability is. There's a 0.0015% chance that the insurance company will pay out a large sum, lose $250,000 because something destroyed the house. But there is a 1 minus 0.0015. That's the rest of it. That's going to be 0.9985 chance that they don't have to pay out anything. So the expected profit, that's our expected value. This time we're talking about not winnings, but profit. Here is going to be our result. Sometimes we have to, the insurance company, I should say, has to give out $250,000, and that's going to happen 0.0015 out of one chance that's going to happen, a 0.15% chance that that's going to happen. Then we're going to have $0 that we have to give out, 0.9985, 99.85% of the time. So this is going to give us a calculation of negative $375. So the insurance company should expect to pay out negative $375 each year for this kind of house. But note that you're giving $500 each year. So total, they expect to make $125 for that individual policy. There's a small chance they pay out a whole lot of money. There's a big chance they don't have to pay out anything and they just get the money that you pay them. So another way to calculate this is to put this $500 into the results. So I just want to show two different kind of ways to look at this. You can either think about paying that you get 500 at the end no matter what, or put it in each result. So here, the exact same calculation is there, but it's a little bit harder to calculate. Here we have negative 249,500 times 0.0015 plus 500 times 0.9985 will give us 125. But the calculations there are a little bit more complicated because you don't have the zero, which is kind of nice. Either is totally fine, and there's really it's just a personal preference. All right, so this has nothing to do with casino games, but talks about different chances of things happening. And I would like to point out this is exactly how insurance companies operate, just in a much more detailed kind of sense. Right? It's not just house destroyed, house not destroyed. There's different policies, different payouts, different kind of things that could happen, different risk assessments. And this is why you have to pay more to an insurance company if you're at risk to destroy a house or destroy a car, whatever it is, because that means that there's a better chance of that happening, and they need to counterbalance that with more money coming their way in order to make profit as a company. All right, so let's go back to games of chance. Talk about another example here. Let's say you're on a game show on TV, and so far you've won $8,000. In the next part of the game show, you're on stage and there's 4 briefcases on stage with you, and you get to choose one of them. One of the briefcase holds $1, one holds $100, one holds $10,000, and then there's one briefcase that says you lose everything. That is, you lose the $8,000 that you have so far. And the game show is saying, do you want to push your luck? Do you want to make more money? Or do you want to just take what you have and leave? So you could decide to not open a briefcase and leave with just the $8,000, but you might be able to get $18,000 total. So let's talk about this game. Let's talk about the expected value of this briefcase game. So we are going to list our outcomes, talk about our results as well, what we expect monetarily to happen, and then our probabilities. So in order to do this, we need to think about every possible thing that could happen. So we could choose the $1 briefcase. I should say the $1 briefcase. And if we do that, we leave with $8,001 because we've had 8,000 so far. Another thing that could happen is that we could win the $100. That means that we would leave with $8,100. We could get lucky and get the $10,000 prize, and then we would end up with $18,000. Or we could get unlucky and we could lose, and we would end up with nothing. We leave with absolutely nothing. So what are the probabilities of these happening. There are 4 briefcases, and they each have an equal chance of getting picked. There's a 1/4 chance for all of those. So the expected value here is going to be 8,001 times 1/4 plus 8,100 times 1/4 plus 18,000 times 1/4 plus 0 times 1/4. So if we do this calculation out, again, we could write this as 8,001 plus 8,100 plus 18,000 over 4, combining fractions. Total, that's going to be 8,525 and 25 cents. So that's our expected value. And what would this, let's interpret this value. This is saying that we would expect to win $8,525.25 if we play. So in this situation, what would you do? And that's honestly a personal choice. It's not like a right way of doing it, right? You could have the mindset that you started with nothing. So, worst case scenario is you leave with nothing. So there's really no reason not to go for it, right? Overall, the expected value is, 0.525 or 525.25 more than what would you get if you would just walk away. So maybe in this situation, there's a better chance, there's more motivation to kind of play this briefcase game because you should expect to actually walk away with more than $8,000. So it's really a personal preference. I think the math shows that you should play the game, but you do risk losing everything. And this is why game shows are interesting, because that's not an easy decision to make, even if you understand the mathematics of it completely. If you would play this game a lot of different times, then it would be responsible to play this briefcase game instead of walk away, because you'd always walk away with more money. So this is not really an answer. It's really a personal preference when it really comes down to it. But we can use the expected value to help us make some of these decisions. So we'll explore some more kind of ideas of expected value. This idea of games of chance and casinos and insurance companies, as well as some other things, have this value, expected value, that helps look at it at a holistic kind of way and helps us make kind of decisions based on that number.